Students, welcome to Computer Organization and Architecture. In today's session, we are going to discuss direct mapping. So, agenda session plan is the discussion of direct mapping. We have some requirements for this direct mapping technique. The first requirement is common for all three cache mapping techniques. We have three cache mapping techniques. First one is direct mapping, second one is fully associative mapping or associative mapping. The third one is set associative mapping. In all three cache mapping techniques, this requirement is strictly followed. Number of words per cache line should be in the power of 2. Number of words per cache line. In a cache line, we have some addressable words, and the number of the words should be in the power of 2. That is, the number of words should be 2 power some number w. Direct mapping requirement is this one. Number of lines also should be in the power of 2. That is the total number of cache lines C equal to 2 power some number L. From these two, we can infer the following statements. W bits are used to point an address in a cache line. L bits are used to point a cache line. The ith, this one is direct mapping. The ith main memory block Bi will be mapped on the jth cache line Lj using the formula J equal to I mod C, where C is the total number of cache lines. In main memory, or the main memory is organized in terms of blocks. The communication between main memory and the cache memory is in terms of blocks. A block will be read from the main memory and that will be placed in a single cache line. Suppose we have a block with a number I, that one is named as Bi. That one is going to be mapped on any one of these cache lines. In direct mapping, we have a formula to find the line J equal to I mod C. So let's see one example. On which cache line the main memory block B255 will be mapped? Consider the total number of cache lines are 16. In a cache, we have 16 lines. Main memory contains n number of blocks. Now B255 should be mapped on cache. On which line that will be mapped if direct mapping technique is used? We have the formula J equal to I mod C. I is our main memory block number, that one is 255. Mod C is the total number of lines available in our cache, that one is given as 16. So 255 mod 16, the answer is 15. So B255 will be mapped on L15. Always B255 will be mapped on L15. This is the rule in direct mapping. Consider the following toy examples. These are not real examples. To convey the concept, I take a very simple toy examples. Total number of main memory blocks and the total number of cache lines of three memory organizations are given below. The first organization, a main memory size is 32. Cache, number of cache lines in the cache is 2. The scenario 2, same main memory blocks, cache line is 4. A third one, same main memory block, number of blocks in main memory is same, 32. The cache line is increased to 8. Apply direct mapping mechanism and find the line numbers for each block B0 to B31, where these blocks will be mapped. That we go to discuss. and you might have observed that the block size or line size is not given. Why? Because that one is not important at the time of mapping. A block is going to be mapped on a single line. Line size will be equal to block size. So the same number of memory units are going to be mapped on cache line. We go to solve these three problems. Lj, by using the same formula, Lj equal to Bi mod C. First scenario. In scenario 1, given B equal to 32 and C equal to 2. So we have two lines. If we apply the formula, we have Lj equal to Bi mod 2. So our answer will be either 0 or 1. Even number of blocks will be mapped on line number 0. Odd number of blocks will be mapped on line number 1. This is a very simple problem. So you can see here in line 0, blocks 0, B0, B2, B4, etc., B30 are going to be mapped. Similarly, in line number 1, B1, B3, B5, etc., finally B31 will be mapped. So this is the arrangement or mapping mechanism if we have B equal to 32 and L equal to 2. Now let's see scenario 2. In scenario 2, B is unchanged, B is 32, C is 4. Again we go to follow the same formula, Lj equal to Bi mod 4. Now C equal to 4, so mod 4. Our answer will be 0, 1, 2, 3. These are our line numbers, L0, L1, L2, L3. Where B, 15 will be mapped. 15 mod 4, that will be 3. So 15 will be mapped on 3. You can see the arrangement. In line 0, B0 is mapped. Line 1, B1 is mapped. Line 2, B2 is mapped. Line 3, B3 is mapped. And then again B4 is mapped on line 0. So in line 0 we have these blocks B0, 4, 8, 12, 16, 20, 24, 28. Line 1, 1, 5, 9, 13, 17, 21, 25, 29, etc. Simple, we have to use this formula Bi mod C. Third scenario. Again, main memory size is not altered, but cache size is increased. C equal to 8. Same formula is used, so we can find the blocks which can be mapped on any one of these cache lines. 0, 1, 2, 3, 4, 5, 6, 7 are our cache line numbers, and 0 to 31 block number. In line number 0, 0, 8, 16, 24 are mapped. Line number 1, 1, 9, 17, 25 are mapped. So now we know how the mapping is occurred. We have some B number of blocks in main memory. We have some C lines in cache memory, and a block is going to be mapped on a line by using this formula. Right. Now obviously we will have a question. Which block resides in a particular cache line now? Why? Because you see here on lines. Now we have a question. Which block resides in a particular cache line now? Why? Because see the scenario. See scenario 1. On line number 0, we may have block 0, we may have block 2, we may have block 4. So totally 16 possible blocks can be mapped on line number 0. So how can we identify which block is currently present in that particular line? Similarly, you see all three scenarios. In each and every scenario, multiple number of blocks can be mapped on a single line. So we should know which block resides on the particular cache line now. How can we know that? The solution is tag bits. Let us consider scenario 2. In scenario 2, any one of a possible 8 blocks may be mapped on line number 0. Line number 0. It may be B0 or B4, B8, B12, B16, B20, B24 or B28. How can we know that? To differentiate or to identify which block is available in a particular cache line, we go to use tag bit. Suppose if the tag bit is 0, 1, 1 for line number 0, then we know block 12 is currently present in line number 0. Suppose line 01 has 001 as tag bit. Now we know on line number 1 block 5 is present. Suppose 101 is the tag line for line number 2, then we know 22 is present in line number 2. Suppose let us consider 111 is the tag bit for line number 3, then we know 31, block 31 is present in line number 3. So the arrangement will be like this. We have 4 cache lines, line 0, line 1, line 2 and line 3. 4 cache lines, and we know the tag bit for this one is 011. The tag bit for this one is 001. The tag bit for this one is 101. The tag bit for this one is 111. Then we know by seeing this tag bit 011, we know 12 is available here. B12 resides in this cache line. 001 is the tag for L1. 001 is the tag for L1. On L1, we may have any one of these 8 blocks, but as the tag bit is 001, we know or we ensure block 5 is available on line number 1. Similarly, this one is 101. 101, line number 2, 22. Block 22 is present in line number 2. 111, 31. Block 31 is available in line number 3. So that is the importance of tag bit. Without tag bit, we don't know which block is available on a particular line, cache line now at present. So let us see the summary of direct mapping. Address length is n bit, meaning the processor will place n bits on the address line. That n bit is actually T plus L plus W. T tag, L line and W word in a particular line. So T plus L plus W bits, that n equal to T plus L plus W. Number of addressable units in main memory. We have our processor here and we have our main memory here, main memory. These two are connected through various buses. Now let us see only the address bus. So the size of address bus is n, meaning here we can have 2 power n addressable units. 2 power n words or bytes are available. Block size, this main memory is organized as some number of blocks, B0, B1, etc., etc. Finally some B n or BM, something like this, right? It is named like this. The block size, how many addressable units are present in a block, that will be equal to line size is, we can get that one from this information W, to 2 power W words. Once we know this one 2 power w, then we know the number of blocks present in our main memory. Similarly, in the other way, if we know the number of blocks, we know how many addressable locations are available in a block. Number of blocks, suppose let's assume we know this 2 power w. Number of blocks in main memory is 2 power n minus w. Why? Because 2 power n is the total number of addressable units and 2 power w is the number of addressable units per block. So totally 2 power n minus w blocks are available in main memory, and we know n equal to t plus l plus w, so minus w 2 power t plus l, tag plus tag bit, the sum of tag bit and line bit, 2 power t plus l. Number of lines in cache is 2 power l, that one is derived from this one 2 power l. Size of the cache is 2 power l plus w. Why? Because in a single line we have 2 power w addressable units. Totally we have 2 power l lines. So 2 power l into 2 power w, that is 2 power l plus w. This is the size of our cache. Width of tag, we can get that one from this formula, n minus l plus w. We can get this l from the number of lines. We can get this w from the number of words per line. So we can get these two, and we know this n t we can obtain. How the bit fields are arranged? Memory address is divided into 3 fields. First tag field, second line field, third word field. This is the arrangement. MSB bits are tag bits, and the middle group is line. LSB bits are word. Number of bits in the word field equal to log base 2 number of words per line. Suppose if you have 8 words in a particular line, then how many bits will be allocated for word field? Log 8 base 2 log 2 power 3 base 2, 3 log 2 base 2 equal to 3 bits will be allocated. Number of bits for the line field, how many bits will be allocated for the line field? That one depends on the number of lines. Log number of cache lines base 2. Suppose if we have 4 lines, 4 cache lines, then 2 bits will be allocated. 8 lines, 3 bits will be allocated. Tag bit size equal to memory address bits minus L plus W. We can obtain W, we can obtain from L, from our design. So tag bit size equal to memory address bits minus L plus W. Bits per block minus bits per line. Bit fields in direct mapping. Let's see example. Let's consider the scenario 2. Consider 256 addressable words are available in main memory. 256 addressable words are available. It implies 8 bits are needed to identify one address. Address bus size will be 8, n equal to 8. We are referring scenario 2, meaning B equal to 32, 32 blocks are available, and C equal to 4, 4 cache lines are available. So main memory is divided into 32 blocks. Hence 256 by 32 equal to 8 addressable words are available per block. In other words, block size is 8. 8 addressable units are available per block, so block size is 8. Hence line size is also 8. Block size equal to line size. So 3 bits are needed to identify an addressable word from a single line. A single line has 8 words. If we want to identify one word, then we need 3 bits, 0, 0, 0, means first word, 111 means last word. 3 bits are needed. As 4 cache lines are available, according to our problem, we have B32 and C4. So as 4 lines are available, 2 bits are needed to differentiate a line, or 2 bits are needed to identify a line, right? L equal to 2, and tag bits are 8 minus 2 plus 3 is equal to 3. 3 bits are used as tag bits. Now the 8-bit address is organized like this. First 3 bits are available for, are allocated for tag bits, right? 7th bit, 6th bit, or D7 or A7, A6, A5 are used as tag bits. The memory address will be like this: A7, A6, A5, A4, A3, A2, A1, A0. This is our 8-bit memory address. A7, A6, A5, these 3 bits are used as tag bits. The next 2 bits indicates a particular line. The last 3 bits point a word. Let us consider these 2 addresses: 1000100, 1010100. This is block 17. This one is consider this one, these 5 bits. This is 16. This one is 1, 1, 2, 4, 8, 16, right? In a block 0002 111, 8 addresses are available. So at present we won't bother about this one. It belongs to the same block. The block number is B17. This block number is, this is 16. Here we have 4. Here we have 1. So 21, block 21. Block 17 and block 21 both are mapped on the same line, line 1, right? We have discussed that one here. Block 17 and block 21 are mapped on the same line, 01, right? Both addresses will be mapped on the first word of line 1. Why? Because here also I have 000, here also I have 000. First word 000, second word 001, last 8th word 111. So this content will be mapped on this line. This content is also mapped on this line, right? The cache hit or miss, whether the intended address is available on cache, that is considered as cache hit. If the intended address is not present on that particular cache at the time, that is considered as miss. Cache hit miss is decided by tag bit, this one. See, this one is our tag bit, right? If the tag bit is 100, then on this address we have 1000100. Only this content is available here. Suppose if we search this one, that one is not available. Why? Because tags are not matched. So this one is in detail given in this diagram. This is our memory address N. That one is divided into 3 fields: T field, L field, W field. What will happen? First, the line field will be considered. It will go to a particular line, or the memory organizer, that memory management unit, that will go to that line, that cache line, and it will extract the tag bit of that particular cache line. That tag of cache is compared with the memory tag. The tag of cache is compared with the memory tag. Memory address is divided into tag field, line field, word field, right? This tag is going to be compared with this tag. If both are same, equal, 1, let's consider this operation is equal to operation. equal 1 if match, that indicates a hit. 0, then it is no match. If these two tags are equal, then we have a 1, a hit. At the time what will happen? It will use this bit field to identify the particular word. If there is a miss, then what will happen? It will go to main memory block. See, block equal to T plus L, that we have discussed earlier, right? Block equal to T plus L. So it will go to that particular block and fetch the block and place the block in the particular line and then fetch the data from cache. So this is the procedure to read or write a particular memory address if cache is present and the direct mapping technique is used. So now let's see some problems. Consider an 8-bit address is issued by processor to locate a memory. Assume B equal to 32, T equal to 3 bits, L equal to 2 bits and W equal to 3 bits for the following 3 problems. Meaning it is scenario 2. Consider an 8-bit address. So how many memory locations are available? 2 power 8 memory locations are available, that means 256. 256 memory locations are available. Assume B equal to 32, number of blocks 32. So what is the size of a block? 256 divided by 32, this is equal to 8. 8 memory locations, 8 memory addresses are present in a single block. In turn, 8 memory addresses are present in a single cache line. So W equal to 3. L equal to 2 bits, meaning we have 4 cache lines. C equal to 4 cache lines. So obviously T will be 3. On which cache line address 137 is available? Address 137, on which cache line address 137 is available? Address 137 will be issued by the processor in a bit pattern, 8-bit pattern. So write the 8-bit pattern, 137 681 34 0 17 0 8 1 4 0 2 0 1 0. So 137 is 1 0 0 0 1 0 0 1. You can check like this. This one is 1 2 4 8 16 32 64 128. So 128 plus 8 136 plus 1 137, right? Now these 3 bits are considered as tag bits. These 2 bits are considered as line and these 3 are considered as word. So on which line the address 137 is available? On line 1. On line 1. On which cache line address 137 is available? It is available on line 1. Processor wants to read the content of address 234. Here everything is assumed as decimal, right? Processor wants to read the content of address 234. State the condition for cache hit. What is the condition for cache hit? For that again we have to write 234 in binary. 29 2s are 58, 14 2s are 28, 7 2s are 14, 3 2s are 6, 1 1. So 128, 64, 32, 16, 8, 4, 2, 1. 1, 1, 1, 0, 1, 0, 1, 1, 1, triple 1, 0, 1, 0, 1, 0. Yes, this is right. So now the question is, what is the condition? The condition is the tag bit of line 1 has to be 111. That is the condition. If the tag bit is something other than this 111, we have 7 other possibilities 0, 0, 0 to 110. If the tag bit is any one of this, then we have a cache miss. Suppose a cache miss occurs when processor tries to access the address 47. Find a range of addresses which will be updated. Okay, we have to write this 47 again in terms of binary. 47, I'll write that one here itself. Okay, go to screen. 47, 128, 64, 32, 16, 8, 4, 2, 1, 47, 1, 32 plus 8, 47. This is 47, right? We have a miss. So, what are the addresses going to be mapped on cache now? These addresses are going to be mapped on cache now. 00101, 00101 is the block number, right? And in this block, these memory addresses are available 0000 to 111. What is this one? 32 plus 8, 40. This one is 47. So 40, 41, 42, 43, 44, 45, 46 and 47 are going to be mapped on the cache. A cache can hold 64K bytes. Data is transferred between the cache and the main memory in blocks of 4 bytes each. So W equal to 2. We know this one. Main memory consists of 64 megabytes. Log 64M base 2. This is the number of bits issued by the processor. Log 2 power 6 2 power 20 base 2. Log 2 power 26 base 2. 26. So we have these things now. N equal to 26. W equal to 2. Right. What else we know? A cache can hold 64K bytes. 64K bytes. This is going to be arranged in these many numbers. Number of lines. C equal to 64K divided by 4. In a single line, 4 memory locations are available. So number of cache lines are 16K. So what is L? L equal to log 16K base 2 log 2 power 4 into 2 power 10 base 2 equal to 14. So we know C equal to 16K and we know L equal to 14. So we have these informations from the problem. Now let's go to the subdivisions one by one. How many blocks are in main memory? Totally we have 64 mega addresses in main memory. One block has 4 bytes. So totally 16 mega blocks are available. B equal to 16 mega. How many lines are in cache? That already we found. C equal to 16K. How many bits are allocated for tag? Tag T is N minus L plus W. N is 26 minus L is 14 plus W is 2. So 26 minus 16, 10 bits. 10 bits are allocated for tag. What are the lower and higher values of tag in hex? Meaning the minimum and maximum values. 10 bits are available. The minimum is 0 0 0 0 0 0 0 0 0 0. The last one is, or the highest one is 1 1 1 1 1 1 1 1 1 1. In hexa means this is 0 0 0 H 3 F F H. So the range is 0 0 0 H to 3 F F F H. The lower one is this one, the higher one is this one. Right. Now we have solved some 4 problems. Let's see the last topic of cache. State the principal merit and demerit of direct mapping technique. Principal merit we can get it from this one. Right. Actually we have 16 kilo lines, meaning 16 into 10 24 lines in cache. It's very big. So many cache lines are available. But if we use direct mapping, we go to check only one line. Only one line. Why? Because the particular block will be mapped on a single line if we use direct mapping. And if the MMU is going to check the tag bit. The memory management unit is going to check the tag bit or whatever component we have, that is going to check this tag bit. If the tags are mapped, then cache hit or cache miss. So immediately or in a very fast manner we know whether a particular memory is present in a cache or not. That is the principal merit. Very fast. And we have a formula, so organization is also simple. What is the demerit of direct mapping technique? Suppose let's consider our toy example. C equal to 32 and L equal to 2. Then on line 0, B0, B2, B4 etc. are going to be mapped, B16. Let's assume processor wants to get or access an address which is present in B0 at time t equal to 0, and the processor wants to access an address which is present in B2 when t equal to 1. Again processor wants to access this one t equal to 2, again wants to access this one at time t equal to 3. Alternatively it needs these two addresses again and again, some 1000 times or 10,000 times, right? Now what will happen? Initially B0, let's assume B0 is available in line 0. B2 should be available in line 0 only. B2 should not be placed in line 1, even though line 1 is present. Now what will happen? First this will be accessed. First we have a cache hit. At the time of accessing this one, the address from B2, B2 is not present. So we have a cache miss. So we will go to, or the memory management unit will go to main memory, it will fetch B2 and it will place B2 on line 0 and it will access. Next again it needs to access data from B0. Now we have a catch miss. B0 will be placed. Again we want to take something from B2. Again we have a catch miss. So only one time we have a catch hit. After that continuously we have a catch miss. The worst part of this one is place is available. L1 is available. Suppose in L0 B0 is placed and L1 B2 is placed, then these two are present in cache. So no catch miss will occur for this kind of scenario. But now we cannot use L1 to hold B2. Why? Because a formula is available, that is direct mapping technique. So B2 should be mapped on L0 only. B0 should be mapped on L0 only. Right? So this problem is called a thrashing problem. Suppose imagine this one, 16K space is available. Now we are using only one line continuously for 2 blocks. Right? Or these 2 blocks are going to be accessed again and again very frequently. Then what will happen? Even though we have a vast cache, we cannot utilize that one effectively. This problem is called a thrashing problem. We discussed the direct mapping technique. The starting addresses of blocks, which will be block number followed by 000. Right? Starting addresses of blocks, which could be mapped on a particular line, is known. So all the addresses which can be mapped on a block is known. All the addresses which could be mapped on a particular line is known. Principal advantage and disadvantage of cache mapping is discussed. Thank you. We are discussing the elements of cache. The last sessions we have discussed the factors which are needed to design a cache. We have discussed about cache size, cache line size, replacement algorithms, writing policy, whether we need to include an unified cache or split cache. In our last session we have discussed direct mapping. In this session we are going to discuss about the remaining 2 mapping techniques. The first one is fully associative or associative mapping, and the second one is set associative mapping. With that, elements of cache will be over. Associative mapping. In associative mapping, any main memory block may be mapped on any cache line. In direct mapping, a particular block should be mapped on only one line based on the formula J equal to I mod n. Due to that one, thrashing problem occurs. Suppose 2 blocks B1 and B2 are to be mapped on the same line Lk, and suppose these 2 blocks are repeatedly accessed by the processor, then the thrashing problem will occur. Suppose imagine B1 is on this line. Now processor wants to access B2. This B1 should be moved to main memory and this B2 should be written on this cache, meaning a cache miss occurs. Next B1 is accessed by the processor. Now again cache miss will occur. Next B2 is going to be accessed. Again cache miss will occur. So this problem is called thrashing. Even though the cache has many other lines, even though the cache has many other free lines, B2 cannot be mapped on any one of these free lines. B1 and B2 should be mapped on the same line. That is direct mapping. Direct mapping is simple, but it has this thrashing problem. In fully associative mapping, any block, any main memory block may be mapped on any cache line. So, this thrashing problem is avoided. But to recognize the cache miss, all tags have to be checked. Why? Because a block may be in any one of the cache line. So, each and every line stacks should be compared. To improve the performance, all tags are checked in parallel, otherwise the performance will be degraded. So, all tags are compared in parallel in associative mapping. It makes the design complex compared to direct mapping. So, the complexity of associative mapping is more compared to direct mapping, but fully associative mapping eliminates the thrashing problem. The address format of fully associative mapping is considered as given below. Tag, word, only 2 fields are available. In direct mapping, tag, line, word, 3 fields are available. In direct mapping, 3 fields are available: tag, line and then word. But here only 2 fields are available. First field is tag field, the second field is word field. A cache line has k words and w bits are allocated for word field, meaning k equal to 2 power w. If 2 bits are allocated for word, then the cache line has 4 words. If 3 bits are allocated for word, then cache line has 8 words. If a cache line has 16 words, then w will be 4. When the address has n bits, n minus w bits are allocated for tag field, w bits are allocated for word field. Total size is n. So, n minus w bits are allocated for tag. The cache has any number of cache lines. 2 power l for some l is not mandatory. In direct mapping, the number of lines should be in 2 power some positive integer, but in fully associative mapping that is not mandatory. The cache may have any number of lines. The cache may have 5 lines or 50 lines or 500 lines or any number of lines. So, here we can see the cache organization. The memory address is divided into 2 fields, a tag field and a word field. The cache lines have a tag field and the cache lines are having words. So, this is line number 0. The line number 0 has these many words and line number 0 has this tag. Line number j has a same number of words and line number j has this tag. Line number m minus 1, the last line, has the same number of words, for example 4 lines, for example 4 words, and the tag of this one is this one. So, totally m lines are available in this arrangement. To identify whether a particular address resides on the cache, all tags should be compared. See here, this tag, this tag, this tag, everything, all tags are compared with the tag of this memory address. The memory address is divided into tag field and word field, right? The tag field of memory address should be compared with each and every tag of our cache memory. after comparison, either it is going to access a memory from the cache or it is going to access the block from the main memory. When it will access the cache, if there is a hit, if any one of the tag is equal to the memory tag, if any one of the cache tag is equal to the memory tag, then there is a hit. At the time, the word field is used to find the appropriate word. So, this one is considered as hit, 1 is match, 0 is not match. If there is a hit and if there is a hit, then this word will be used to find the appropriate memory address, and this branch is considered as miss branch. So, here the value for this branch is equal to 0 if there is a tag match, meaning miss is 0, there is no miss. If there is no match, then this branch will have one value, no tag is equal to the memory tag. At the time there is a miss, so the block which has the address should be moved to cache and then read. So, that will happen here. The total memory address, the whole memory address is used to identify the block. The block is fetched and the block will be placed in any one of the cache line using some replacement algorithms, and then the intended address will be read by the processor. This is fully associative mapping. So, let us see one numerical example. It is given the main memory size is 16 MB. So, number of bits allocated for address is log 16m base 2, 16 is 2 power 4, mega is 2 power 20, so 2 power 24. So, the number of bits allocated for address is log 2 power 24 base 2, that is equal to 24. So, the address size is 24 bits. The address is going to be divided into two fields, one is called tag field, the second one is called word field. In the problem it is given data are transferred between main memory and the cache in blocks of 4 bytes. So, the block size is 4 bytes. If we know the block size is 4 bytes, then we know the number of blocks available in the main memory. The number of blocks in main memory is equal to the total size of main memory divided by the size of one block, 16 MB divided by 4B, that is equivalent to 4 MB. 4 is 2 power 2, M is 2 power 20. So, 2 power 22 blocks are available, 4 M blocks are available. Any block may be mapped on any cache line. So, to identify one block among these 2 power 22 blocks, 22 bits are needed, that will be the tag size. 22 bits are needed to identify a single block. So, tag size has to be 22 bits. We can get the size of tag in another way also. It is given block size is 4 bytes. One block size is equivalent to one line size. So, line size is 4 bytes. 2 bits are allocated to select a word from a line, meaning the number of bits allocated for word field is 2. So, the remaining 22 bits are allocated for tag fields. Number of bits allocated for tag field equal to 24 minus 2 equal to 22. In either way we can get the number of bits allocated for tag field and word field. Cache size is given as 64 KB. Cache size is given as 64 KB. That 64 is 2 power 6 and k equal to 2 power 10. So, totally 2 power 16 bytes are available in the cache. Number of cache lines is equivalent to number of cache lines is equal to the size of the cache divided by a single line size. Size of the cache is 2 power 16, a single line size is 2 power 2. So, 2 power 14 or 16k lines are available in the cache. Any main memory block among the available 2 power 22 is mapped on any cache lines among the available 2 power 14. So, the address format will be like this. MSB 22 bits are considered as tag, most significant 22 bits are considered as tag, and the least significant 2 bits are used to find the appropriate word. So, totally 24 bits are available. Now, let us see the mapping diagram. The mapping diagram is given here. This is main memory. A single block has 4 bytes of data. So, 32 bits are available in a single memory block. The main memory size is 16 megabytes. In a single block 4 bytes are available. For example, see this 13, 57, 92, 46, this is a hexadecimal number. Each and every hexadecimal number is equal to 4 bits. So, 1, 2, 3, 4, 5, 6, 7, 8, 32 bits are available, 4 bytes. And this, the address for this one is 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0, finally 0 0 0 0. This is the very first address. That address is divided into tag field and word field. For word 2 bits are available, for tag the remaining 22 bits are available. See the next address tag is 0 0 0 0 0 1. The word 0 1 0 2 0 3 are not shown in this figure. Why? Because those addresses are included in this block. The left hand side we have only the block addresses. Very first address of that block is given. So, always in the word field we have only 2 zeros. It is inferred the address 01, 10, 11 are included in this block. So, the size of that block is 32 bits. This one is mapped on this line. What is a tag? 6 zeros. So, 6 zeros are available here. What is a word? 13, 57, 92, 46, that one is available here. So, for example, block 0 is mapped on line 3 F F E, and this one is mapped on line number 0001. This one is mapped on the line number 0000. The idea is any block may be mapped on any cache line. The last cache mapping technique is set associative mapping. Set associative mapping has the strength of direct and fully associative mapping techniques. It has the strength of direct mapping as well as fully associative mapping. The cache has V number of sets. The number V can be represented as 2 power d for some positive integer d. This is a constraint in set associative mapping. The number of sets should be written as 2 power some positive number. Each set has k lines. K may be any positive number. The size of the cache is B into K into 2 power W, where V is the number of sets, K is the number of lines per set, and 2 power W is number of words per line. So, the size of the cache is the product of these two factors. K is written here, the V can be written as 2 power D, 2 power W. The V can be written as 2 power D and this 2 power W is written as it is. So, now the size may be written as K into 2 power D plus W. A main memory block is mapped to any line of a particular set only. This any line of is very similar to our associative mapping. Associative mapping is the other name for fully associative mapping, and only to a particular set is very similar to direct mapping. By combining direct mapping and associative mapping, the set associative mapping has the advantages of the previous two mappings. In direct mapping, the line number is calculated by using a formula I equal to j mod c, where c is the number of lines, this j is the block number. So, by manipulating right hand side, I will be identified, the line number is identified. Only on that cache line this block should be mapped. Very similar to this direct mapping, the set associative mapping calculates or finds a set using this formula. Set number equal to block number mod V. V is the total number of sets available in that cache. For example, the number of sets are 4, then we have 4 sets, set 0, set 1, set 2, set 3. When divide a block by 4, we have the remainders 0, 1, 2 and 3 only. 0, if the remainder is 0, that will be mapped on set 0. If the remainder is 1, that will be mapped on set 1. If the remainder is 2, that will be mapped on set 2. If the remainder is 3, that will be mapped on set 3. but it is different from direct mapping since a set has k lines. The block may be mapped on any one of these k lines. That one is given here, any line of a particular set. For example, when v equal to 8, the block number 32 is mapped only on set 0. Why? Because 0 equal to 32 mod 8. But the block may be mapped on any line of set 0. So, this indicates the characteristics of direct mapping, and this indicates the characteristics of fully associative mapping. So, the thrashing problem may be avoided since a block may be mapped on more than one lines, a freedom is available. The complexity is reduced. Why? Because only one set is going to be verified, only one set is going to be checked to identify whether the block is present or not present. Only one set is going to be verified to determine cache hit or cache miss. A k way set associative mapping has k lines in a single set. A two way set associative mapping means it has only two lines in a set. Four way set associative mapping means it has four lines in a single set. In each and every set we have four lines. A k way set associative mapping has m by k sets when the cache has m lines. In a single set k lines are available, totally m lines are available. So, m by k sets are available, and remember this number should be 2 power some positive integer. K has to be a divisor of m. When k equal to 1, it is direct mapping. When k equal to 1, according to this formula, m sets are available, m lines are available. Each and every set has only one line. So, when a block is mapped on a particular set, actually that is mapped on a particular line. So, this is very similar to direct mapping. Here set has no meaning, set has only one line. So, the block will be mapped on that line only, it has no freedom to be mapped on any more line. So, this is direct mapping. When k equal to c, here we are using m lines. So, instead of this c we can use m. When k equal to m, it is fully associative mapping. When k equal to m, m by m only one set is available. The set has all lines. So, if a block is mapped on that set, that block may be mapped on any one of these m lines, that is fully associative mapping. So, a set associative mapping may be modified as a direct mapping, or it may be modified as fully associative mapping. A set associative mapping has number of sets like this. If it is 1, then that is fully associative mapping. If it is m, this is number of sets, then that one is direct mapping. So, set associative mapping has the advantages of direct mapping as well as fully associative mapping, according to the application the number of sets will be chosen. But a two-way set associative mapping has better performance than direct mapping and fully associative mapping. The complexity is minimized. Commonly used K values are 2 and 4. The main memory address format is considered as given below in a set associative mapping. The main memory address is divided into 3 fields. First field is tag field, second is set field, and third is word field. While checking an address, the appropriate set which is indicated by the bits of set field is chosen. First, an appropriate set will be chosen. All tag bits of the lines of that set will be compared parallel. This is very similar to fully associative mapping. Only one set is chosen, that is very similar to direct mapping. If there is a match in tag, then cache hit. Then the word field, this field, is used to access the word. If not, meaning cache miss, then the word with the block is moved from main memory to any one lines of that set using some replacement algorithms. This is the organization of K-way set associative mapping. Set 0 has k lines 0 to k minus 1. Set 1 has k lines k to 2k minus 1, like that it is going. To identify an address or to check whether an address is present in the cache or not, an appropriate set is chosen. In this organization, set 1 is chosen, and all the tag bits of all lines, the tag bits of all lines are compared in parallel. See, these are the tag bits, right? So, these are compared with the tag bit of main memory address. Now, we have two results. Either the address is available in cache memory or the address is fetched from main memory. First, let us discuss this branch. This is considered as hit. If any one of the tag line is matched, then it gives a 1 if match, 0 if no match. If there is a hit, then this field is used to fetch the particular appropriate word. Similar to that, this branch is working. This branch is considered as miss. When miss is 1, if there is no match, then miss is 1. If there is a match, then miss is 0. Actually, hit is 1. So, if there is a miss, then it will come here. The entire memory bits are used to fetch the field and place it in an appropriate set. So, let us see the same example for the set associative mapping also. Main memory size is 16 MB. So, the number of bits allocated for the address is log 16m base 2. Already we have discussed this. We have discussed the problem during fully associative mapping, same thing. This one is 24. So, the address bus size is 24 bit. Block size is 4 bytes. meaning line size is 4 bytes, block size is equal to line size 4 bytes. So 2 bits are allocated to select a word from a line. The 24 bits are available here. The last 2 bits are used to select a word. Cache size is 64 KB, that one is given here, 64 KB. 64 KB means 2 power 16 bytes are available. 64 is 2 power 6, K is 2 power 10, so 2 power 16 bytes. So how many number of lines are available in that cache? A single line has 4 bytes. The cache has 2 power 16 bytes. So 2 power 16 divided by 4, that one is 2 power 14. 2 power 14 cache lines are available. 2 lines per set, that one is given here, right? 2-way set associative mapping. So 2 lines per set. So how many sets are possible? 2 power 14 by 2, 2 power 13 sets are available. Number of bits allocated for a set is 13. So next field is this one, 13 bits are allocated for set. Totally 24 bits are available, 13 bits are allocated for set, 2 bits are allocated for word. So remaining 9 bits are allocated for tag. The most significant 9 bits are allocated for tags. The next most significant 13 bits are allocated for set. The least significant 2 bits are allocated for word. So that one is given here. For example, consider this address, a 24 bit address, 4, 8, 12, 16, 20, 24, 24 bit address. The 24 address, the 24 bit address is grouped as MSB 9 bits, this 4 bit, this 4 bit and this 1 bit. That one is grouped like this. That one is considered as tag. The next 13 bits, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So 12 bits and this one 13 bits are used to identify the set. The last 2 bits are considered as word field bits. So this address will be grouped like this. The word is available in any one of the 2 cache lines of set number, this number 1 1 1 1 0 0 0 1 0 1 0 1 1. In hexadecimal, this number is represented as, this one is B, this one is 2 and this one is E and this one is 1, 1 E 2 B H. So this address will be available on this set only. That set has 2 lines, this may be in any one of these 2 lines. When any one of the line has tag, this one 0 1 0 1 1 0 1 0 1. If any one of these 2 lines has this tag, then cache hit. If both the lines are not having this bit pattern, then cache miss, and it can be written in a hexadecimal again by grouping 4 bits from the least significant bit. So, that will be 0 B5. The tag field is not having 0 B5, then cache miss. If a cache hit occurs, then this will be used to fetch the intended word. This is the third word. First word is 0 0, second word is 0 1, third word is 1 0, fourth word is 1 1. This is the third word. So, the third word of that line is accessed. If no lines has the tag, then the block except this one, all other bits are used to identify the block, right. A block has 4 bytes 0 0 0 1 1 0 1 1. So, we can ignore this word field. This block will be moved to this set. If no lines has the tag, then the block 0 1 0 1 1 0 1 0 1 1 1 1 1 0 0 0 1 0 1 0 1 1 or the corresponding hexadecimal number is copied from main memory and is placed in any one of the 2 lines of the set 1E 2B in hexadecimal. So, this is set associative mapping. Now, the cache elements have been discussed.